Hello, I'm Ruihong from Tsinghua University. I'm going to talk about our paper, Effective and Efficient Retrieval of Structured Entities. A structured entity is a set of connected nodes, often in a tree structure, labeled with types and contents. For example, a structured entity T1 consists of 4 nodes. For node I134, its type is institute, while its content is University of Hong Kong. Such structured entities are commonly abstract from various source types. For instance, a structured entity in relational database is a collection of tuples connected via primary foreign keys. XML entities are naturally organized in a tree structure. In RDF data, entities could be interpreted as subgraphs. In the emerging scenario of data lakes, direct retrieval on structured entities from various source types becomes an important problem. The retrieval problem is to find the structured entities that are most relevant to the query. Consider cooperation with different customer channels. If we have a structured query entity T13 from some XML documents in the online channel, and we want to find the same person Alice from a relational database in the educational channel, then the result entity T1 is expected. The structured entity is different from the information object consisting of multiple documents without any structure. One structured entity may contain another because of the hierarchical structure, and it leads to the overlapping contents between parents and children. For example, the institute entity T2 is a child of entity T1, and the term home appears both in the parent entity T1 and the child entity T2. The question is the term more representative in the parent entity or the child? If we simply add up the score of each term, a term is always more representative in the parent, since the score in parent also contains the score in children. Then child entity could never be retrieved, and the parent is always returned. The other concern is about the structural inconsistency. A straightforward idea is to evaluate the graph at a distance between entities. However, as we mentioned before, entities T1 and T13 from different data sources have very distinct structures, but indeed denote the same person in real world. In our proposal, we also consider the turn scores of structured entities. By interpreting the content of a node as an unstructured document, we represent each node by a vector of turns. The score of turn W in node T could be evaluated by any IR score function in document retrieval. Then the score of turn W in the entity combines the score of all the nodes appearing in the entity. For example, if we consider the count of the turn as its score, then the score of turn home for node O42 is 1, and the score in entity T13 should combine the score in node O42 and R62. Then we define two types of similarity scores between entities. The turn vector similarity is calculated by adding up the product of each turn score between two entities, and it is usually interpreted as the cosine of the angle between vectors. The other way is to aggregate the word embeddings weighted by turn scores to form the structure entity embedding, and the similarity is evaluated by the cosine similarity between two embedding vectors. And the most important part is the design of the score combination function. However, the existing simple score combination strategies may fail to distinguish the entities with parent-child relationships. As we mentioned before, the score combination by sum is to sum up the scores of all nodes appearing in T. A direct result is that parent entity always has a higher score than any of its children. As shown in the example, the child entity T2 denoting the same real-world entity as T14 cannot be retrieved, since its parent entity T1 gets a higher score by the simple sum combination. Instead of simple sum, the combination with normalization over the size of entity T is computed as the average of non-zero scores. However, in this time, a term in the parent entity T can never be as representative as in the children sometimes. For example, T13 and T2 with higher similarity scores by the size normalization combination will be erroneously returned. However, the truth is that T13 and T1 denote the same real-world entity. The structure-aware combination in our proposal is enlightened by an observation. If most entities with the same structure share contents between head node and their children, the shared terms in children are likely to be representative in parents. We define the entities sharing the same structure as an entity family. The entity family can be used for evaluating how large a type of nodes share with its children. It can also be used for efficient pruning. The coefficient law is learned from all the entities in an entity family to tell the difference of a term's importance in the parent and children entities. For example, the entities T2, T6, and T10 share the same structure, and the coefficient law is 7 divided by 30. Then the hierarchy smooth combination function is defined recursively with the help of coefficient law, and lambda is a smooth factor in the range of 0 to 1 on weighting the parent and child entities. As in the example, the score by hierarchy smooth combination function can derive the correct matches of T13 and T1 and T14 and T2. To discuss the properties of our structure-aware combination, we rewrite it with regard to smooth factor lambda. It is a linear function on the variable lambda. We use theta to denote the difference between the pre-computed coefficient law and the actual ratio of scores in children entities to the score in the head node. If theta is larger than 1, the pre-computed coefficient is larger. The head node does not share as much as other same structure entities with children in actual. Then the term is more representative in the parent. If theta is less than 1, the pre-computed coefficient law is smaller. The term is not as representative as most other terms in the entity family. The term could be more representative in some child entity. For efficient entity retrieval, we use property of monotonicity for ranking. We build an inverted index on terms over nodes ranked by the node scores with the same node types. Then the threshold at this level of the term in an entity family is given recursively like the structure-aware combination function. By aggregating the thresholds on all the nodes referred by the query entity, we could obtain the threshold for the similarity scores between the given query and the entities in each level. We conduct experiments on 2 datasets. Article dataset consists of scientific papers collected from DVLP and Sightseer. Movie dataset collects movie information from IMDb and Freebase. To simulate a real-world data lake, we intentionally add both textual and structural noises to the datasets. The datasets are split into multiple parts. Each one uses a different structural representation. We also randomly replace words in the dataset by their synonyms. The experiment studied many factors in the data that may affect the performance, including the number of entities and different structures. Our proposed methods show the highest precision and keep the time cost low. That's all about our presentation. Thanks for listening.